So far in Chapter 2, you've looked at pretty simplistic motion, right? Things that are pretty much going from point A to point B at constant velocity, right? Something's moving 50 meters per second for 10 seconds. How far has it moved during that time? Okay, that means they're moving at constant velocity. So whenever we're using that velocity equals distance over time equation, that means that the object is moving at constant velocity. It's not speeding up, it's not slowing down, it's just moving. Basically, you've got your cruise control set on your car, okay? It's moving at constant speed. Are we clear about that?
Yep.
Okay, that's when we use that equation, when something is moving at constant speed. So now these position versus time graphs have the ability to show us a little bit more complex motion. The object might be moving at constant speed, then they come to a stop, then they move backwards, then they do this, blah, 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 blah. Okay, so these graphs allow us to look at a little bit more complex motion in one place. Okay? So position versus time graphs are considered one of our motion diagrams. You looked at some motion diagrams in yesterday's notes or last class notes. But these position versus time graphs are another example for us of motion diagrams. Okay? They show us an object's position at a certain time interval. We should see on a position versus time graph that our axes are labeled. So in this one, I think they got cut off. Okay, and it might tell you that it's measured in meters, or it might be measured in centimeters, or it might be measured in whatever length unit we want. But position versus time here on the bottom, I think your time might be covered up a little bit, but time should be in seconds or hours or whatever. Okay, so this isn't the best graph I've ever seen. We want to make sure that it has labels and it has units on those axes as well. Okay, but you have to make sure that we're really paying attention here to understand that it's position versus time. We're going to look at two big types of graph: position versus time and velocity versus time. So those axes labels become really important in interpreting the graph. Okay, so let's look at our first position versus time graph. It shows us displacement versus time, or the object's position against what time interval we're looking at. Okay? And realistically, the most important thing that we can gather from a position versus time graph is the object's velocity. Okay, we can calculate velocity based on the graph alone. Okay, and the way we do that is to find the slope of our line. Okay, to calculate velocity from a position versus time graph is going to be to find the slope. So let's take a look at this example. This isn't quite to your handout yet, but I just want to take a look at what this one is asking. Okay, so what we're seeing here is that with every half of a second, this object has moved 1 meter. Okay, do we see that? With every half of a second, our object has moved 1 meter. And what's our equation to find slope? Yeah. Final y, or y2 minus y1 over x2 minus x1. Okay, this also looks like delta y over delta x. Okay, because we know delta means change in, or final minus initial. So if I want to calculate the slope of this line, can I just pick any 2 points? I can pick any 2 points on this line. Okay, so let's calculate the velocity of this, and we're just going to pick any 2 points. Okay, so let's say my 2 points here, my coordinates are 2, 4, and this point here is 0.51. All right, so I need to calculate my slope here. Okay, and that slope is going to tell me what physics variable. What's the slope going to tell me? So if I want to calculate velocity, I'm going to take change in y over change in x. Okay. So if I want to calculate velocity, I want to take my final y, which is 4, minus my initial y, 1, over 2 minus 0.5. Okay. Which is going to give me 3 over 1.5. 2 meters per second. Okay, If I go look at my graph now, I'm basically telling you that this object has moved 2 meters after 1 second, right? It's moving 2 meters every 1 second. So if I look at the 1 second time interval, we could expect my position to be what?
2 meters.
2 meters, and is it?
Yep.
Yes. Okay. So this slope of a position versus time graph tells me the speed at which I'm moving. So whenever I have a straight line on a position versus time graph, that means I have constant velocity. Okay? In this particular instance, is my position moving forward or backward?
Forward.
Forward. Okay? So I have a positive slope. So positive slope equals positive velocity, which means I'm moving in the forward direction. Okay, so you might want to put that in your notes as well. Positive velocity, positive position, right? I'm moving forward. You can see from that graph. Okay, so positive slope equals positive velocity, which means I'm moving in the forward direction. Take a look at this graph that's on your handout. Okay? The slope of the graph, we know, tells us a velocity. Tells us our speed or our velocity. What does the negative slope here tell us? So where do we see negative slope? From what time interval? You can look on your sheet or look here. 2 to 6. So if I say 2 seconds to, okay, really 5 seconds, right?
Yeah, you're right.
Okay. So 2 seconds to 5 seconds is a negative velocity. What's that mean about my motion? Is it moving forward? Is it moving backwards? Is it stopped? What's it doing?
Accelerates.
It's moving backwards, not necessarily decelerating. Doesn't necessarily mean it's slowing down. It means it's moving backwards at constant velocity. Okay, remember straight lines here mean constant velocity. Okay, so let's talk through just what's happening in this motion before we get too into this. Okay, from 0 to 2 seconds, which happens to be here to here. Okay, 0 to 2 seconds. Take a look at your graph also. What do we see happening here?
It's not moving.
It's not moving. It's still at its origin. It's not moving right here. If we calculated the slope of this line, what would we get?
0.
0. So that means we have no velocity, which means we're not moving. Okay? If we go from 2 to 5 seconds, what do we see happening here? We're going backwards, and are we moving at constant velocity? Yes, because we have a straight line. Now what are we doing from 5 seconds to about 7 seconds? Moving forward. Yeah, we're moving forward at constant velocity. Did we pass our starting point? Yes, okay? Because we crossed the x-axis here, it means we passed our starting point again. Okay? What happens from 6 seconds to about 12 seconds? Sorry, 7 to 12. What's happening? We stop. Okay, are we at our starting position? Are we in front of it, behind it? We're in front of our starting position, but we stop for 5 seconds. Okay, from 12 to 14, what are we doing?
Going backwards.
Going backwards. And are we going backwards slowly or really quickly? Constant speed, but is it fast constant speed or slow? Quickly, right? Look at how steep our slope is. So think about it this way. We covered a lot of distance in a really short amount of time, right? We covered 1, 2, 3, 4. We covered 9 meters in 2 seconds, right? That's pretty quick. Or 3 seconds, whatever that time interval is, okay? So we cover a lot of distance really quick. A steep slope, let's write this down on your notes as well. So a steep slope means fast velocity. Could mean in the positive direction, could mean in the negative direction. Depends on which way that slope is going. So we know a shallow slope. Do you know what I mean when I say shallow?
Yeah.
Okay, shallow slope equals a relatively slow velocity. Okay. What are we doing now from 14 to 16 seconds? Right in here.
Stopping you.
Right here, 14 to 16.
Oh, I thought you were saying.
That's okay.
Forward.
We're moving forward, and are we moving at constant speed? Yeah, it's pretty quick, right? Pretty quick. From 16 to 18 seconds, what are we doing? We've stopped. Good. And then from 18 to 19? Forward at constant velocity. And then from 19 to 20? Stopped. Okay, and we're technically back at our starting point here. Okay. Yeah, so they did a lot of forward and backward motion here, ended up where they started. Okay, very good. Position versus time graphs could also tell us moving up or down. Okay, if you're talking about something that's in the air, we can think about it in terms of that too. Okay, we just have to understand positive direction is either forward or east or up, or it could mean a lot of those different things, right? All right, questions here. If we wanted to interpret this graph in terms of y equals mx plus b, we know that our y-axis is our displacement or our position. Our slope, or m, is equal to velocity. Our x is time, okay, because that's our x-axis. And then our y-intercept is basically our initial position, or d sub I, right? Initial position, initial displacement. Does that make sense? We could always start our motion from here instead, right? We don't have to start at our origin. We could start at 2 meters east or whatever, okay? It doesn't have to necessarily start at 0. So that would be our initial displacement, okay? Question. Okay, so go ahead and calculate velocity. This is the one that's in your handout. I want you to find velocity from 1 to 3 seconds. And of course, to find velocity, what should we be calculating? The slope, right? Calculate the slope. Be careful that you read the axes correctly. Just because it's 2 intervals doesn't mean that it's 2 meters, right? Our y-axis is labeled at 20, 40, and 60. Are we agreeing with 20 meters per second? Okay. We can check ourselves a little bit. If we start to look at our graph, we see an increase here, right? Up 20 meters over 1 second, right? That's the way you can kind of check yourself on the graph. Some graphs aren't quite as clear as this one, but that makes an easy check for us, okay? But everyone's getting it to come out at 20? Okay, let's calculate now velocity from 4.5 to 6 seconds, where we start to see this negative slope. What's the negative slope here tell us? We're moving backwards at constant speed or constant velocity. Okay, so let's call this one at 4.5. Okay, this. Slope. We should be expecting a negative slope. Good. And we get about negative, negative 26.6, 0.67, 0.7. However you round that is really okay. I don't like fractions, however. Okay. So I do like the decimal point. And what's our units for velocity? Meters per second. Good. Is I want you to write out in words, right? Describe to me what's happening at each of these sections. From point A, this object is sitting still, it's moving whatever. Point B, it's doing this, and C, it's doing this. So I want you to first and foremost do that, and then we'll start looking at some calculations.
It's going forward.
Good? Is it speeding up, slowing down, constant velocity?
Constant.
Yeah, good. Constant velocity. So constant positive velocity. Okay, or moving forward at constant velocity. There's lots of ways that you can say that. Okay, but velocity being positive or negative tells us the direction, right? If I have negative velocity, it means that I'm moving in the negative direction. If I have positive velocity, I'm moving in the positive direction. So there's a couple ways you can say that. Yvanka, can you tell me what's happening at part B? Good. Standing still. All right, stopped. It's at rest. There's lots of different ways we could describe that. And Jordan, can you tell me at point C?
It's moving back constant speed.
Good. Moving backwards at constant speed. Good.
Very slowly.
Pretty slowly. Good. All right, so if I was going to compare just the speed, essentially, of A to C, which of those would give me a greater speed value, not counting direction? A would give us a greater speed value. It has a greater slope, so we're covering more distance in a shorter amount of time. Okay, very good. What if I have a position versus time graph that looks like this? Let me draw it a little bit better. Okay, what do we mean by opposite? First of all, they're going backwards. Okay, so we're moving backwards. Negative direction. Are we speeding up or are we slowing down? We're slowing down. Good, because we're starting with a really steep curve and we're slowly getting to a more gradual. Okay, so we are slowing down in the negative direction. And do we see why it's in the negative direction? Because our slope is generally pointing downward. Okay, so we're going backward or going toward our origin again. Very good. Very good. Okay, so now, let's say, last one here, my position versus time graph looks like this. Okay, so now it's got a little bit more complex motion. Okay. Let's see here. A, B, C, D, E. Okay, let's see, Sarah, tell me what's happening during portion A. Good. At B, we are stopped. We're not moving anymore. Eric, what's happening at C? Is it speeding up or moving at constant velocity? Moving forward at constant velocity. So I want to make sure we understand the difference. Speeding up and moving at constant velocity are two very different things. Okay, think about when you're driving. Speeding up means you've got your foot on the gas, you are increasing your speed. Constant velocity means you have the cruise control set. Okay, those are two very different things, so I don't want you to get those confused. Speeding up and moving at constant velocity are two different things. So point C here means we are moving at constant velocity in the positive direction. It just happens to be really fast because our slope is really steep. Okay? All right, Caleb, can you tell me what's happening at point D? It stopped. Good, it goes from about here to here. Okay, it stopped, we're not moving. And Jordan, what's happening for E? Okay, and what am I doing? Yeah, you're right. Okay, you're right. We are speeding up in the backward direction. Okay, so now we're moving backwards and speeding up. Yeah, yeah. Curved is what we call acceleration, so we're going to talk about acceleration here in the next section. But I just want you to start thinking about it in terms of speeding up or slowing down. So yeah. the curve is going to tell us basically if it's accelerating, basically speeding up or slowing down in the forward or the backward direction. Okay. So here, I could probably draw the graph so it looks a little bit nicer, but essentially we're going from a shallow slope or from a stopped position to a really steep slope. So we're increasing our speed, but it's in the negative direction. Okay, on the same page here? All right, very good. So the next type of graph that we're going to look at is going to be a velocity versus time graph. Guys, thank you. So next, a velocity versus time graph is going to tell us basically the rate at which our speed is changing or the rate at which our velocity is changing. Okay. Changing technically. Okay, so the rate at which our velocity is changing is what is displayed on a velocity versus time graph. Okay, so I want to take a look at this first position versus time graph that's listed right up here. Tell me what's happening in this motion. This is position versus time. So what's happening? Going forward at constant velocity. We're moving in the positive direction at constant velocity. This down here is showing us the exact same motion. This is velocity versus time graph. This is a straight line, which means we're moving at constant velocity, 200 centimeters per second. Okay? And we know it's positive because this is above the x-axis.
Wait, would it be going, wouldn't you should be on sail?
Right here?
No, because that's
Oh, versus.
Yeah, this is velocity versus time. So here our velocity is 200 centimeters per second.
Okay.
And so that's the difference there. So, what'd you say? Oh, right here. Right here. Yeah, we'll have velocity versus time graphs that extend below the x-axis, and then we'll be able to see them go negative. Okay, just like you can have position versus time graphs that go below the x-axis also. If you move behind the origin. Okay, but your x-axis is right here on the time intervals. Okay, so if we had something that was below the x-axis, that would mean that we're moving backwards. Okay, listen carefully. I need you to understand this part. If on a velocity versus time graph we see something below the x-axis, that means we have a negative velocity, which means it's moving in the negative direction. We clear?
Right.
Okay. What if I have a velocity versus time graph that looks something like this?
It's constant, but
no, it's slowing down.
Yeah, it's slowing down. It's slowing down. So ignore this line for right now. That's okay. Okay, this is slowing down because it's approaching zero velocity, right? As time goes on, it's getting closer and closer to zero velocity, right? We're going from 200 meters per second to 100 meters per second to 0 meters per second. We're slowing down, okay? So there's two different things that we can look at here in terms. If we wanted to see something that was slowing down on a position versus time graph, right, it would look like this. So we would have a curve, right? Position versus time graphs are the only ones with curves. I want to make that clear. Only ones with curves. We will not have curves, no curves, on velocity versus time graphs. No curves. Don't do it. Now, let's take a look. Here we're still looking at velocity versus time graph. So now let's talk through what's happening in the motion. Okay, is this one on your handout or not quite yet?
yes.
Okay, so I want to write. It's not. Okay, so I want to talk through at least what's happening in this graph. You don't have to necessarily draw the graph up, but if you want to do a rough sketch, that's fine. I'm going to write these down so we have an idea. From point A to point B, what do we see happening in this graph? Yeah, it's accelerating. We can start using that term. I'm going to define that term, acceleration, and what that means next class. But I want you to start thinking of in terms of, is it speeding up? Is it slowing down? What's it doing? Okay, so let's keep from using the term acceleration just yet, because I'm going to define that next class in the physics world. But right now I want you to look at from A to B. Is it speeding up? Is it slowing down? Is it moving in the positive direction? What do we see? Speeding up, right? And it's above the x-axis, so we know all of this right here is happening in the positive direction. So all of this is moving forward. Okay, we're going upward.
Now that we're on velocity versus time, speeding up is appropriate.
Yes, because our velocity is going from 0 meters per second to 20 meters per second. So we are getting faster. Okay, so from A to B, we're speeding up. Okay, from B to C, what are we doing? Constant speed. We're not coming to a stop. We're moving at constant speed right here, and it's at 20 meters per second. Okay, so from A to B, we're speeding up because we're going from 0 meters per second to 20 meters per second. We've got our foot on the gas right there. Okay, from B to C, we set the cruise control. Okay, from C to D, good, we're speeding up again. C to D, speeding up. Okay, from D to E, what are we doing? Constant speed. Okay, from E to F, we are slowing down, but are we still moving in the positive direction? Yes, that's really important. A lot of us will think here negative slope means always moving backwards. That's not the case. Okay, here we're still moving in the positive direction, so we're just slowing down. So slowing down, but it's still positive direction. Okay, from F to G, what are we doing?
Constant speed.
Constant speed. And here when I use the term speed, it's interchangeable with velocity. I want you to understand that. It's just that happens to be what we're writing, but those are interchangeable right at this point. Okay, from, oh sorry, F to, or G to H. I don't know my alphabet. What am I doing?
Speeding up.
Speeding up, good. Okay, any questions about where these came from? Yeah? No? Seconds on this graph. Let's go ahead and find that. Displacement from 4 to 5 seconds.
Constant, oh wait,
Displacement we're going to calculate by finding the area under this graph. Okay? So I want to articulate one other thing. Area under the graph, but it's only to the x-axis. Okay, so you find the area under the graph. So from 4 to 5 seconds, we see that my line, my slope looks like this, right?
yeah.
So I want to find the area from the x-axis to that particular point.
So instead of saying find area under the graph, can you say find area under the x-axis?
Yeah, but it's from the x-axis to whatever point that is on the line. Yeah, yeah. Okay, so I need to find the area of a triangle. Yep, 1/2 base times height. So this is 1 second. This side of my triangle is how many meters per second? -2. It's important that we include the negative here because we're moving in the backward direction, aren't we?
Yes.
Yes. Okay, we know we're moving backwards because we've crossed underneath the x-axis. We're moving in the backward direction. So during that time, if I take 1 times -2 divided by 2, gives me -1, technically centimeters because this is measured in centimeters per second. Okay, so during that time interval, I have traveled backward a total of 1 centimeter, -1 centimeter. Okay, and do we know why it's centimeters?
Because that's what the.
Yeah, it doesn't have anything to do with how we calculate it. It's just that the graph is reading in centimeters per second, which means our displacement would have to be centimeters.
1/2 base times height.
You guys good?
Yep.
Do that on this graph. So let's talk through what's happening from 0 to 2 seconds. What do we see happening in this motion? Speeding up, right, in the positive direction. From 2 to 3 seconds, what do we see? Constant speed. Good. We're not stopping. We're moving at a constant speed. What are we doing from 3 to 4 seconds?
Slowing down.
Slowing down, but are we moving in the positive direction or the negative direction? Positive. We're still above the x-axis at this point. Okay? So essentially, we've gone forward. Now we hit the cruise control. Now we slow down. But we're still moving in the forward direction. Okay? From 4 to 5 seconds, what are we doing? Backing up, right? We're moving backward pretty quickly. And then from here to here, what are we doing? No. Be careful. What do we see it going? Are we moving forward? No, we're still moving backward because we're still below the x-axis. This is where it gets tricky. So we went backward really quickly from 4 to 5 seconds. From 5 to 7 seconds, We're slowing down, but we're still moving in the negative direction, so we're still moving backward. Okay? That's a little bit more confusing. Okay? Just because our slope is positive doesn't mean we're moving in the positive direction. It means we have positive acceleration, but that doesn't, I'm going to get to kind of what that means here later today. Slowing down in the negative direction. So we're moving backward, but we're slowing down. So from 4 to 5 seconds, my object went really quickly in the negative direction. Now it's slowing down, but still moving backwards. Okay? We know it's slowing down because our velocity is starting to approach 0. Okay? Right here, the x-axis is 0 meters per second. So as we start to approach that x-axis, that means we're slowing down. Since we're below it, that means we're moving still in the backward direction. Okay? That's a little trickier, right? Velocity versus time graphs are a little bit trickier. Okay, this is the one we looked at earlier. We already talked through what was happening in this motion. Slope tells us acceleration, and we find that using the equation delta y over delta x. Okay, so that part probably needs to go into your notes. I think this one is on your handout, right? Okay. No? Does it not on your handout? Okay, well that's okay. Slope of your line on a velocity versus time graph tells you acceleration. We find that by calculating the slope, delta y over delta x. Okay, on any of these position versus time graph or velocity versus time graph, time's going to be our independent variable. Okay, why do we think time might be our independent variable?
It's always just.
Yeah, it's going to go. It's always going to go, right? We're not manipulating that in any way. It doesn't depend on the velocity in any way. So time's going to keep marching on, right? And we're going to see what happens to our velocity, our position, in terms of that time. Okay. Okay. So on this on this velocity versus time graph, we know that if we want to find the displacement, we find the area under the graph. So let's find the displacement from 5 seconds to 8 seconds on this graph. 5 seconds to 8 seconds. So I don't know if this graph is on your handout or not. Okay, so I'm just going to do it up on the board here. 5 seconds is right here. Eight seconds is right there. Okay, I want to find how far this object has traveled. What's its displacement during this 3-second time interval from 5 seconds to 8 seconds? Are we on the same page about what this question is asking? Okay, so find the area here. Is this a shape that we know how to find the area of? That's good, because it's a rectangle. I'm glad you said yes. Okay, so this side of our rectangle is 3. This side of our rectangle is 40. 3 times 40 is 120 meters. Okay, how do I know it's meters and not centimeters?
Because that's what it says meters per second.
Meters per second. Okay, if I take meters per second times seconds, that's going to give me just meters. Okay. So this is a way you can kind of check yourself pretty roughly, but this works fine. If I'm moving from D to E, what's happening in my motion? What am I doing? I'm moving at constant velocity for this time interval of 3 seconds. From D to E, I'm moving at constant velocity. And I'm moving constantly at 40 meters per second. Okay, so 40 meters over 3 seconds, 40 meters plus 40 meters plus 40 meters gives us 120 meters. Okay, so that's a way to check ourselves. Yeah, you could, but what happens if we want to look at, let's say, find the displacement from 0 seconds to 5 seconds.
You have to add a triangle or rectangle.
Yep, let's try it. 0 seconds to 5 seconds. Let's find our displacement here. Is this a shape that we know how to find the area of right off the bat? Not so much. But, yeah. This is a triangle. This is a rectangle. A triangle. Okay. So let's try it. Go ahead and do this one on your own. I think you can do this on your own. I think that you can do it on your own. Hey, do these 3 on your own. Finding acceleration means we calculate the slope. Your graph is a little bit harder to read, but I need you to understand that this is the x-axis right here. Okay? This is the x-axis. And time is labeled by 2 seconds. Okay? Not by 1 second intervals. Okay, so if I find the slope from here to here, I'm going to take my coordinates and I'm going to say delta y over delta x gives me 2 minus 0 over 2 minus 0. Okay, because this coordinate is actually at 2, 2, not at 1, 2. Okay, I see several people did not have that correct. Okay, now if I want to find displacement from 8 seconds to 10 seconds, that means I find the area. So here's my 8 seconds to 10 seconds. I find the area from the x-axis to that line. Okay? Which means I find the area of the triangle, which is 2 times 2 divided by 2, which is really 2 meters.
That's it.
2 meters. So this was 1 meters per second. What's my velocity from 16 to 18 seconds?
2 meters per second.
Constant, and it's at negative 2 meters per second. So finding the velocity from a velocity versus time graph means you just read the graph. That's it. Okay? Just reading the graph.